In this lesson we're going to be going over how we can define the pressure of a gas using this concept of particles. So we're going to try to relate the idea of pressure from dynamics to the idea of the pressure of a gas. And we're going to be making use of the idea of an ideal gas, but we will go over just what we mean by an ideal gas in the next lesson. So our objective in this one is just to define pressure in these terms. So the way that we're going to do this is we'll have a look at a simulation which sort of demonstrates what we mean by an ideal gas, and we can use this simulation to get a sense of how a pressure is produced by the particles within an ideal gas. Okay. Now, the pressure of a gas is the result of collisions between the molecules of the gas and the walls of the container. When the particles collide with the walls of the container, they exert a force on the walls of the container. This force will result in a pressure, because the pressure is just the force exerted divided by the area over which that force is exerted. And typically in a gas we'll have a huge number of particles colliding with any given wall of a container per second. This results in a significant pressure on that wall, which is the force divided by the area over which the force is applied. So just to show you how this works, I'll just pump a tiny number of particles in like this. So here we have just 7 particles. And the particles will move around randomly, and they will have differing kinetic energies, and the average kinetic energy, as we've already heard, depends on the temperature. Now, these particles will collide with each other, and they'll collide with the walls of the container, and each time a particle collides with the wall of the container, it will exert a force on the wall of the container. So we can see, for example, let's follow one of these particles along. So we'll just pick a suitable one, like this one, for example. Or, in fact, let's go with this one. It'll collide with the wall and it'll bounce back. So this particle here was traveling in this direction, it collided with the wall, and then it bounced back. The initial momentum of the particle depends on the mass and the velocity. So the initial momentum was in this direction, and the final momentum also depends on the final on the same mass and on the final velocity. The final velocity is in a different direction, so there's been a change in the momentum. The change in momentum is the final momentum minus the initial momentum. And because the final momentum is in this direction, and the initial momentum was in this direction, but we need to subtract it, so we have the final minus the initial, which will give us a change in momentum that is to the right for this particle. And so we can see that the particle experiences a force as it collides with this left wall to the right, which means that the particle must have exerted a force to the left on the wall. Now, that's using Newton's third law. If the particle exerts, if the wall exerts a force on the particle to the right, then the particle must exert a force on the wall to the left. Okay, we'll let this play a little bit longer, and you can see that this is going on all the time with all the particles. Every time they collide with the wall, we get a change in momentum of the particle, which means that there must have been a force on the particle, which means that the particle must have exerted a force on the wall, which means that there must be a pressure on each of those walls. Now the pressure in this particular instance is pretty insignificant, because we have so few particles. However, what we can do is pump in some more particles here, so I'll just do that. And now we can see that we have significantly larger number of collisions with any given wall per second. And this means that the force over any given time is going to be significant, and that means that the pressure will also be significant. In fact, the pressure will be roughly constant throughout. You can see here that the pressure is fluctuating slightly, but the pressure becomes more and more stable the more particles we have. And in here at the moment, I don't know, I'm estimating, but we might have about 100 particles. In a container of sort of macroscopic size, we would have many orders of magnitude more particles than we have in this situation. So the pressure would be virtually stable here. Now, if we choose a wall to have a look at, so if we choose this bottom wall, for example, we can see that over time, lots and lots of particles are colliding with the wall over any second. If we increase the number of collisions per second, so for example by increasing the temperature, which we can do here, so as we increase the temperature, we can see all the particles move faster, which means that they'll collide more often with the walls, which means that the pressure that we measure here will increase. So if you keep an eye on this pressure gauge, I'll add a little bit more heat. You can see that the pressure rises as we add heat to this gas. Another way that we can increase the pressure is by reducing the size of the box. So this again means that we have more particles per unit volume, which means that we're going to get more collisions with the walls per unit time, which means that we get a sharp increase in the pressure here. So just to sum up, the pressure of a gas is determined by the force that the particles exert on the walls of the container of the gas, and the more collisions that we have with per unit time between the particles and the walls, the greater the pressure will be of the gas. So pressure in mechanics is defined as the force per unit area over which that force is applied. So we can write this as an equation. P is equal to F over A, where F is measured in newtons and A is measured in meters squared. And so pressure should be measured in newtons per meter squared, although we abbreviate that with the unit Pascal. Now the pressure, for example, due to the air above you, so this is gravity pushes the air down on top of us. The pressure that exerts on us is about 1.01 times 10 to the 5 pascals, or 101 kilopascals. In a gas, this force, the force in this equation here, we have P is equal to F over A, that force comes from the collisions of the gas molecules with the walls. The pressure will decrease if the force is spread over a larger area. The pressure also decreases if the force itself becomes smaller. So this force will become smaller, for example, if the number of collisions of particles with the wall per second decreases. It'll also become smaller if the energy that the kinetic energy that the particles have on average becomes smaller, because the energy imparted to the wall will be smaller if the particles are moving less quickly. The force that's applied to the wall will become smaller if the energy is smaller, the kinetic energy. In the next lesson, we'll go over in more detail what we mean by an ideal gas, and we'll get a clearer sense of how temperature relates to the motion of the particles, and how varying the temperature, the pressure, and the volume of an ideal gas affects the dynamics within the gas.